Hello everyone, welcome to the Methods 3-4 lecture. My name's Kaif, I'm going to be your lecturer for today. So a little bit about myself, I did Methods 3 and 4 back in 2022 and I ended up getting a 45. So I'm hoping that through this lecture here I'll be able to impart some of my knowledge and help you guys receive a similar score this year. Now, before we hop into the lecture, I just want to give you guys a quick overview of what we do here at ATAR Notes. So, since 2007, we've been offering heaps of free resources to make students just like you really thrive in their studies. Free lectures just like these ones, we've been offering them since 2015, and of course, free resources like this, they're in line with our mission here at ATAR Notes to help students as much as possible. Now, we have tons of free resources for you, like study notes, lectures, discussions, videos, everything's there. You can check out these things over at atarnotes.com if you want more details. Uh, if you're looking for even more support though, we've got you covered with some paid resources. So this is ATAR Notes Plus here. We've got study guides, flashcards, practice tests, so on and so forth. All stuff that'll help you take your study to the next level and ultimately really excel in VCE. All right, with that being said, let's jump into the lecture. So, if you want it straight, uh, here's some points of advice for you. The first thing you want to make sure you have is a good foundation. You can talk to your teachers, you can talk to your peers, look at different textbooks, even look at the internet to understand the basic concepts. This will all help you build towards a really good foundation, and then you can fill in the gaps in that foundation and really have a holistic understanding of the Methods 3-4 content. Now, don't afraid to be a nerd. If you really want to excel in methods, you need to show a commitment to it beyond the average student. So that's doing things like looking at YouTube videos, going to Wikipedia and just reading stuff there, messing around in Desmos at the back of maths class whenever you're bored. Things like that will help you, yeah, fill in those gaps in your foundation and give you a better understanding of the content. Now, all throughout the year, you really want to make sure that you practice. It's the only thing that matters. You have to have exposure to a wide range of different questions and know how to organize your time when it comes to doing those questions. Uh, of course, with the end of your exam, you only have a few hours to rush through so many questions. So, making sure that you're confident with the questions you're exposed to and know exactly how to save time when writing out your answer, that'll go a long way to getting that illustrious 40 plus score. So throughout the year, chapters, reviews, past SACs, exam papers, checkpoints, force your teacher to be on their toes about giving you all of these different resources. It goes without saying, make sure you do exam papers leading up to your exam, at least 10 whole papers. That's what I did personally. And make sure that you also put questions that you got wrong with their annotated solutions in your bound reference. I'll go into a bit more detail with the bound reference at the end of the lecture, but make sure you do that. And then the final thing is to have calculator skills. Make sure you know all your shortcuts. You'll develop these over the course of the year, but really make sure you're confident with using your calculator because the second part of your exam is going to be very calculator intensive. Okay, let's move into some content. So today we're going to split the content up into two blocks. First block is going to look at just like a 1-2 review, as well as looking at higher polynomials like cubics and quartics, and then also looking at different functions like hyperbolas, trunci, so on and so forth. Block 2 then will be about transformations as well as exponential and log functions. And then I've just got a little bit of bonus content at the end. Now, all throughout, I want you guys to be asking questions in the chat. I'll be there replying as quickly as possible. So please, if there's anything that you don't understand, ask a question in the chat and I'll get back to you as quickly as possible. All right. Starting off with linear equations, we're going to do a very brief review here. Some formulas that you have to understand from last year is first off the distance formula. So that's this first formula here. And that just tells you the linear distance between two different points. So if you know their coordinates, you'll be able to find that linear distance using that formula. The second formula is the midpoint formula. This will tell you the point directly in between those 2 points. using that formula. The third thing is the form of a linear equation, y equals mx plus c. This should be drilled into your head by now, but if it isn't, really make sure you know that one. And then the gradient intercept form of uh, the linear of a linear equation. I didn't use this much. I mostly just relied on this, but feel free to be comfortable with both. You might find that this has advantages over this in certain situations and certain questions. All right, so yeah, that was our review of linear. Again, I'm expecting you guys to be very comfortable with linear equations by now. Uh, Polynomials where we want to focus a lot more of our time. So that's quadratics, cubics, and quartics. Now, we have polynomials, the definition of a polynomial. It's an expression with a variable x raised to integer powers. Now, what is an integer? It's a whole number. In this case, we're looking at positive whole numbers. So 1, 3, 600, they're all integer numbers, positive integer numbers. And when we raise x to that power, we get what's called a polynomial. In methods 3 and 4, you're going to have to know exactly how to sketch these functions, how to solve for x when the function equals 0, factorize these functions, and find rules given a particular graph or given some information about a particular polynomial. So you need to get very, very familiar with the shape of the graphs of the polynomial, as well as just some general properties of polynomials. And we're going to be exploring that throughout this lecture. Now note that every polynomial has what's called a degree. This is the highest power present in the polynomial. So if we look at these three examples here, 32x to the 7 plus x to the 5 minus x, the degree here would be 7, because that's the highest power that we have present. In the second example, we can see the highest power is 2, so the degree of this polynomial is 2. And in this case, the highest power is actually 0. If you can imagine an x to the 0 tacked onto this root 3, that would still technically be a polynomial. So in this case, it's a polynomial of degree 0. Okay, so yeah, value of the highest power present. Now, in terms of sketching polynomials and solving for polynomials when they're equal to 0, we're going to first look at quadratics, and then we'll look at cubics and high polynomials after that. So with quadratics, yeah, there's two kinds of questions that you're going to generally get. And it's going to be either a quadratic that's equal to 0 and you have to solve for x, or you're going to have a question that asks you to sketch quadratic, which also involves solving for the quadratic when it's equal to 0, because that's how you find the x-intercept of the quadratic. Of course, we'll get a little bit into that later. But this table gives us the different forms of quadratics and also shows us what information we can take away from it, which is especially important when we're sketching the question. So I've labeled that row with a little star here. With the turning point form, it looks like this. And the info that it gives us at face value, just looking at the equation, it'll give us the turning point, which is at the coordinates h and k. So if this was y equals a times x minus 3 squared plus 4, then our turning point is 3 and 4. Factorized form looks a bit like this. The face value information that it gives us is the x-intercepts, b and c. And then expanded form gives us the y-intercept, which is the value c. We'll look a little bit more into this key info that it gives us at face value in the next slide. One thing I also want to touch on though is when we set each of these expressions equal to 0, then there's a particular method that we have to use to solve for x. In the turning point form's case, we rearrange for x. In factorized form, we have to use the null factor theorem. So each one of these linear factors, either x minus b or x minus c, is equal to 0 by the null factor theorem. And in expanded form, we can either use the quadratic formula, or we can convert this expanded form to factorized form or to turning point form, and then use these methods that I've described here. Okay, so we've first got turning point form and factorized form. In terms of just looking a little bit into more detail on that face value key info that each of these forms gives us. So the turning point form tells us where the turning point is. So graphically, it would look something like this. That's the turning point right there, H and K. And yeah, it says here that if A is greater than 0, then it's going to be an upright parabola, so like a smiley face. But if A is less than 0, then it's going to be an inverted parabola, so it's going to go down like this, like a sad face. We'll look a little bit more into that when we look at transformations, but generally with quadratics, those are just some key things you want to watch out for. It makes it easier for you to visualize how the parabola is going to look. We also have factorized form. So again, it tells us the x-axis intercept. So in this case, we have an intercept at B here and then an intercept at C here. Okay, so that's all for quadratics. Now we've got higher polynomials. So this table here, it describes the forms of cubics, polynomials of degree 3, but generally these forms will also apply for higher polynomials like quartics, even quintics, but you won't have to study those. Those are outside the scope of study design. Just cubics and quartics you'll have to worry about. Now, something you'll notice is that this table is very similar to that table that we saw a couple slides ago, this one here, to do with quadratics. Which is good because it means that there's a lot of information that crosses over from quadratics to polynomials. The only thing that you should note though is when we're solving for x with the expanded form, when it comes to cubics and quartics, we're no longer just using the quadratic formula. We instead have to factorize via long division to get to factorized form. And the way we do that is using the rational root theorem and then the factor theorem. And then from there, we can apply the null factor theorem to solve for x when this cubic is equal to 0. Another thing I want you guys to notice is with the inflection point form, this is now telling us where the inflection point is at face value. So this is a little bit different from a turning point, and you guys might have a bit of experience with this already from your 1-2 study, but we'll go into it a little bit now. Please make sure to ask any questions if you've got any along the way. All right, so let's talk a bit more about the additional features of a cubic that you have to watch out for. For the most part, it's the same stuff, right? So we're talking about x-intercepts, y-intercepts, turning points. One thing you actually have to start worrying about with cubics as well, though, is what we call stationary inflection points. So this is where, if you look at this diagram here, it's where the graph approaches a point and then begins to kind of flatten out. Eventually it reaches a point where it has 0 gradient. So that's right there in the center. It's running flat, parallel to the x-axis. But then immediately starts heading back in the same direction it came from. So this is what's called a stationary point of inflection. And something you want to make sure you don't do is don't confuse it with a point of inflection. Now, points of inflection in general are points of the graph where the steepness of the graph reaches a maximum or minimum. So you can see here, if we look at this graph, the steepness of the graph is decreasing. Eventually it reaches 0, so it's reached a minimum, and then it goes back up. So that's a point of inflection. This is also a point of inflection right here, though, because we can see here at this point, the steepness of the graph is going down, it's getting more and more negative. Eventually it reaches a point here where the gradient is at its greatest negative value. I know it's a bit of a double negative there, but it reaches its greatest negative value, and then it starts the gradient starts increasing towards positive values again, and eventually the graph starts going up again. So this right here is a point of inflection. For those of you learning Spec Math, you're going to need to know these, but in methods, you just need to know that, well, you just need to know what a stationary point of inflection is. And it's a case where an inflection point happens to have a gradient of 0. That is the inflection point is flat. So you can see here, this is a stationary point of inflection because the gradient is flat. Well, it's zero here. That's one thing you want to watch out for, stationary points of inflection. The other thing you want to be familiar with is the general shape of a cubic. You can see here, it's nothing like a quadratic, right? Whereas quadratics, it's just going down, then going up, and going up and then going down. Cubics have a particular characteristic shape. It's a mountain. You can see a mountain there, and then a valley. Now this doesn't always apply. Sometimes you might have just a bit of a wiggle like this. It's not really a mountain and a valley. Uh, but just remember that it can have any one of these forms. In general, just remembering that it's a mountain then a valley will help you out a lot when it comes to tackling questions involving cubics. Uh, okay. Now moving on to quartics. It's a quadratic but with a squarer base, and there's not much more that can be said there. You can see it looks like a quadratic. It comes down and then it goes back up. But you can see how it's a bit flatter at the bottom. So it comes down and then it flattens out and then it goes back up. Now, the thing is, it can still have turning points. Well, I mean, you can see in this diagram here, it has a turning point, but it can also have stationary points of inflection. Looking down at this graph here, we have a stationary point of inflection right here. It goes up to that point and then gets flat and then it keeps going the same way. Uh, you can also have situations where you have three different turning points, in which case you get, like here, you have an upside down W. You might have a not upside down W, just a normal W looking shape. So in general, just remembering you can have either U's or W's for positive quartics. So that's equations with the greatest power being 4 and no negative sign out front in this x4 term, x to the 4 term. This is going to take the shape of a U or a W. Okay, so in terms of identifying when a stationary point of inflection occurs, just by being given the equation of a polynomial, there's actually going to be some very clear signs that, like if a polynomial has an inflection point, it's going to show up in the factorized form of the polynomial. So if we have a particular polynomial, say we have a quartic, and we convert it to factorized form, if the factor has this shape, or has this form, so x minus a, then the graph is going to cut through the x-axis at the point A. If we have that factor raised to the power of 2, so it's a quadratic factor now, then the graph is going to come down and approach A at the x-axis. It's going to touch A and then it's going to come back the same way it came from. So it's kind of like a quadratic. Now, if the factor is raised to the third power, that's when we get a stationary point of inflection. And these are the, like I said before, they're the only kinds of inflection points you're going to have to worry about. The stationary kind of inflection points. So that's that there. All right, so just as a little bit of an exercise, what I'm going to do is I'm going to help you guys figure out how to sketch this cubic right here. So we have y equals x to the 3 minus 4x. The first thing we want to do is identify what form this polynomial is in. Now we don't have any brackets, so it's definitely not factorized form. What else? It's not stationary point form because that's the form where we have some kind of linear factor raised to the third power. So this is going to be expanded form. The face value info we can get from expanded form is the y-intercept, as we saw in previous slides. In this case, the y-intercept is going to be 0 because it's given by the constant term out here, which is just 0. So we can write here y-intercept equals 0. The x-intercept, what would we do to solve this is set this expression equal to 0. So we have 0 equals x cubed minus 4x. And then we need to think about how we can factor it. So with a with a polynomial in expanded form, remember with cubics, we have to convert it to factorized form and then apply the null factor theorem. So that's what we're going to do here. In this case, we don't have to resort to the rational root theorem and the factor theorem, but we'll go into that a little bit later. So in this case, we can see a common factor between these two terms is x, so we can factor that out. We'll write x out the front here, and then here goes x squared, because x squared minus x is x cubed. And then here we write minus 4, because negative 4 times x will give us negative 4x. What we can then do is use our difference of two squares and reduce this further into its linear factors. So x squared minus 4, that's the same as x squared minus 2 squared. So that means our factors will be x plus 2 and x minus 2. Then we can apply the null factor theorem. So this tells us that x, well, the first x value we have is negative 2, because we have this factor x plus 2. Or we have x equal to 0, or we have x equal to 2. The x equals negative 2 comes from this factor, the x equals 0 comes from this factor, and the x equals 2 comes from this factor. That's the x-intercepts. Now the turning points, again, you might have a little bit of practice with this from your 1-2 study, in which case this will be useful to you just as a quick reminder. With the turning points, remember, we're just looking for where the derivative is equal to 0. So we know that the derivative is going to be, we have x cubed, so the derivative of that is 3x squared. You bring the power down and then subtract 1 from the power. And then the derivative of negative 4x is minus 4. Then we can just say at the turning points, dy dx equals 0. Therefore, 3x squared minus 4 equals 0. And then we can state that x squared is equal to 4 over 3. So x is equal to, what is that, plus or minus square root of 4 over 3. Just doing a little bit of simplification, this is going to be plus or minus 2 over root 3, so it'll be 2 root 3 over 3. Okay, yeah, that looks right. Okay. Yeah, okay, cool. So we've got our x values here. We can then just plug those into our equation to get the y values. So when x equals 2 root 3, I feel like I've done something wrong here. 2 over root 3. No, that's correct. Okay, 2 root 3 over 3. Y is going to equal 2 root 3 over 3 cubed minus 4 2 root 3 over root 3. Running out of space here, but you would go on to simplify that, and eventually you would state your turning points and their coordinates. And then this will be useful in sketching the graph. So it's going to look something like this here. Now, we're going to now move on to some formulas that you're going to find useful when it comes to converting polynomials from expanded form to factorized form. So yeah, we're going to look at these formulas, and then we're going to go on to learn how to use the rational root theorem and the factor theorem to factorize some other cubics in expanded form to factorized form. I'm getting caught up on my own words there. Okay, so these formulas are very useful. Please memorize them, because whenever you find an opportunity to use them in your working, they're going to save you a lot of time. So for cubics, you have x cubed minus a cubed. that can be factorized into x minus a times x squared plus ax plus a squared. So that is, let me get my pen back. There we go, my mouse back, sorry. You can see we've got x minus a, so the linear factor is also x minus a. And then because we put a minus here, we're going to put a plus sign in the quadratic factor here. So x squared plus ax. And that's kind of vice versa for x cubed plus a cubed. We can factorize that into x plus a and x squared minus ax plus a squared. Now, for any polynomial, if you're looking to expand it, then you can use Pascal's triangle. What I mean here is, if we look at this formula, x plus a squared, this is the perfect square formula. You get x squared plus 2ax plus a squared. But how do we know what these coefficients are? In this case, 1, 2, and 1. We just look at the third row of Pascal's triangle. So 1, 2, 1, we see it there. For cubics, the expansion formula is x cubed plus 3a squared x plus 3ax squared plus a cubed. And the way I got those coefficients is looking at the fourth row. So whatever power you're raising a linear factor to, look at the row number on Pascal's triangle, but add 1 to it. You're looking at that row. And for those of you that don't know, Pascal's triangle is just formed by adding up the two numbers above it to get the current number. So in this case, in the case of 2 here, we do 1 plus 1, and that gives us the middle number here, which is 2. In the case of 6 plus 4, we have 10. So on and so forth. That pattern just continues down the line. So either you can use that, or you can just remember the cubic, quartic, and quadratic expansion formulas. So this is the quadratic one here. Just remember the cubic and quartic equivalents. Okay, so now we're going to look at the rational root and then the factor theorem. So, I mean, what is the importance, first of all, of factorizing a polynomial in expanded form? It allows us to solve for x when the polynomial is equal to 0, because we first convert it to factorized form, and then we apply the null factor theorem. The rational root theorem and factor theorem are a really good set of tools that we can use to achieve that. So the first thing is, with the rational root theorem, it's this statement that for a polynomial equation, possible solutions are given by x equals d prime over a prime, where d prime is all the factors of d and a prime is all the factors of a. That's a typo there. So this is a bit confusing, but we can look at it with reference to an example, and that'll hopefully help it make more sense. So in this case, we have this polynomial here, 3x cubed minus 1. If we're looking for potential solutions to it when we set this polynomial equal to 0, then the solutions are going to have this form right here, d prime over a prime. D prime is all the factors of d. So in this case, our d value is 1. So all of the factors of 1 is, well, it's just 1 and negative 1. Because 1 times negative 1 is, negative 1 times negative 1 is 1, and 1 times 1 is 1. So 1 and negative 1 are factors of 1. Our a prime value here is 3. It could be 1 or 3, because the factors of 3 are 1 and 3. So we can do 3 times 1, or we can do negative 3 times negative 1. Those are all factors. So putting d prime, all our possible values of d prime over all our possible values of a prime, we're either going to get plus or minus 1. So that's going to look like negative 1, or plus or minus 1, that's the factors of 1, over plus or minus 1, because that's also a factor of 3, and so that's going to end up being plus or minus 1, as we see here. Or it could be plus or minus 1/3 by that same rationale, where instead our a prime value is 3, because that's a factor of 3. So we use the rational root theorem to just discover a couple potential solutions to a given polynomial, and that'll help us better guess the correct solution and save us a lot of time when it comes to substituting in random guesses until we find something that works. So the factor theorem is something that we use to make these substitutions. It states that for a given polynomial p, if p of negative a over b is equal to 0, then ax plus b is a factor of that polynomial. So again, it's helpful to look at this with reference to an example. If we have p of 1 over 2 is equal to 0 for a given polynomial p, then that means that 2x minus 1 is a factor of p. So what this means is we just substitute 1 over 2 in for x, and if it all ends up reducing down to 0, then that means that 2x minus 1 is a factor of that polynomial. Knowing one factor is really important though, because if you know one factor to a cubic equation, then you can separate it into a linear factor and a quadratic factor. And we know how to factorize quadratic factors down to their linear factors as well. And so eventually we're going to end up with the cubic completely in its factorized form. Okay, so one other thing we need to take note of is equating coefficients. So if two polynomials are equal, then each matching coefficient must be the same. And we've got an example there. X squared minus 4 equals ax squared plus bx plus c. If this statement is true, then that means that, first of all, the coefficients of the x squared terms are equal. So that means that the 1 out front here of this x squared term is equal to the a out front of the x squared term on the other side. That means a is equal to 1. Similarly, we can see that the x squared terms are going to be equal, and that tells us that b is equal to 0. In this case, we have, you can imagine there being a plus 0x term here, and so that 0 is going to be equal to b. And then c is equal to negative 4. So now that we have all these tools in our arsenal, we can use this to fully factorize a polynomial. I've got a general set of steps here that I followed personally. And I would suggest that you follow it too, because it really condenses everything down into distinct steps that are easy to follow. So first step is to substitute guesses for x until p of x is equal to 0. So again, with those guesses, we can use the rational root theorem to narrow down our guesses. Taking this example here on the right, we've got p of x equal to x cubed plus x squared, blah, blah, blah. Our possible solution for x, remember we take the possible factors of 24 and we divide them by the factors of the coefficient in front of the x cubed term, which in this case is 1. So in this case, we're just looking at all the factors of 24. So that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, 6, so on and so forth. Eventually, after a couple guesses, substituting these values in for x, you'll find that negative 2 is the value for x for which this polynomial is equal to 0. So p of negative 2 is equal to 0. The next thing we do is we use the factor theorem to rewrite the polynomial as the product of two factors. So again, looking on the right side here, since p of negative 2 is equal to 0, by the factor theorem, that means that x plus 2 is a factor. So we can rewrite the polynomial. First we start off writing x plus 2, and then we know that there's a quadratic factor left, ax squared plus bx plus c. We don't know the values of a, b, and c, but we can then use our knowledge of equating coefficients to find those values. So we can expand this out, x plus 2 times ax squared plus bx plus c, and because it's equal to our original polynomial here, x cubed plus x squared, blah, 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 we can write this statement here, step 3, and then equate our coefficients. So a is equal to 1, you can see that there. B plus 2a is equal to 1, but because a is equal to 1, we can substitute that in and find that b is equal to negative 1. Using that same rationale going forward, we find that c is equal to 12. Then we can factorize the final quadratic factor. So we know what the quadratic factor is. We can substitute our values a, b, and c. And then we just finish off by factorizing that further into linear factors. And there we go. We've converted our polynomial from expanded form into factorized form. Again, I know a lot of this is confusing, so please make sure you're asking questions in the chat. Okay, we have a question. If x plus a is a factor of 4x cubed minus 13x squared minus ax, where a is any real number except for 0, then what are the factors? Okay, so I'm going to get my pen out here. Oh, what's happened? There we go. First of all, we need to rewrite this polynomial in a way that we can justifiably apply the factor theorem, because this is what it's asking us to do. It's asking about a factor. So let's write let p of x equal 4x cubed minus 13x squared minus ax. Okay. Now we can write if x plus a is a factor of p of x, then by the factor theorem, yeah, p of negative a, so because x plus a is our factor, we're taking negative a, must equal 0. I think there's a typo in the question. It should be asking prove that x plus a is a factor of this expression here. So p of a is equal to 0. So if we actually write out what p of a is, it's going to be 4a cubed minus 13a squared minus a times a. So this is going to be 4a cubed minus 13a squared minus a squared was 4a cubed minus 14a squared. Yeah, no, I've just realized the question should be asking find the values of a for which x plus a is a factor. Okay, so in which case, yeah, we're finding a set of values for a. We know this is equal to 0. So again, we can just factor out a squared as the common term here. We have 4a minus 14. So therefore, either a squared, and therefore a is equal to 0, or 4a minus 14 is equal to 0. That's applying the null factor theorem. Then rearranging for a, we're going to get a is equal to 14 over 4, which is 7 over 2. So those are our two values for a, for which x plus a is a factor of this particular polynomial. All right. We're now moving into some sketching practice. So we need to sketch this polynomial here. First of all, what form is it in? It's got brackets, so it's most likely in factorized form, and that would be true. So in which case, since it's in factorized form, the information it gives us at face value is the x-intercepts. In this case, we have the x-intercepts at x equals 1, because we have 1 minus 1, 1 minus x. So if we set x equal to 1, then this would collapse to 1 minus 1, which is 0, and so the graph would be equal to 0 as a result. So x equals 1, and x equals negative 2, and the negative 2 just comes from the x plus 2 term. Y-intercept, we have to find that. So when x is equal to 0, we have y is equal to 1 minus 0 times 0 plus 2 squared. And that's just going to be, well, 1 minus 0 is 1. 0 plus 2 is just 2, so 2 squared, that's going to be 4. Okay. Turning points. Yeah, it might be worth doing the turning points too. just for the sake of completeness, turning points. First of all, we find the derivative. Before we find the derivative, we need to expand this out. So I'll just do it up here. We have y equals 1 minus x times x plus 2 squared. So that's 1 minus x times x squared plus 4x plus 4, which is equal to, let's see, that's going to be x squared plus 4x plus 4 minus x cubed minus 4x squared minus 4x. And then if we collapse those terms down, we're going to get negative x cubed, what is that, minus 3x squared plus 4. Okay, so we have now this in expanded form, so now we can take the derivative. We have negative 3x squared. So remember, bring the power down and then subtract the power by 1. And then we have minus 3x squared here, so this is going to be negative 6x. And then we have 4, which obviously doesn't have, well, it has a derivative of 0. Okay, so at the turning points, dy dx is equal to 0. So therefore we have 0 equal to negative 3x squared minus 6x. We can factor out an x there. In fact, we can factor out a 3x there, so we get negative 3x. Oh, actually, we'll change that to negative 3x. So we're factoring out a negative 3x. Forget about that line. Let's just start a new line here. Negative 3x, we have x, and we have plus 2. Okay, so null factor theorem, x is equal to 0 or x is equal to negative 2. I'm just going to move my working up to here now. When x is equal to 0, y is equal to 4. We know that from when we found the y-intercept. And then when x is equal to negative 2, we know from our x-intercepts that that is going to be, oh, where's my pen gone? That's going to be y equals 0, because we have an x-intercept at x equals 2, right there. So we know now the turning points. We have one at 0 and 4, and negative 2 and 0. We know what the y-intercept is, y equals 4, and we know what the x-intercept is, or the x-intercepts are. So it's x equals 1 and x equals negative 2. Now note, one of the steps which I did was actually redundant, and that is finding the turning point for at the point x equals negative 2. Because if we look here, we have a quadratic factor, and if we go back to that particular slide, where is it? This slide here. It tells us whenever we have a quadratic factor, we're going to have a turning point. So going back to our question, this is information that we essentially already knew. Now, we can go ahead now and plot out our points and then plot out the actual graph itself. So we have a y-intercept at 4. We have that there. So I'm going to label this 0 and 4. We have an x-intercept at 1, which is right here. This is 1 and 0, and then we have an x-intercept also at negative 2. Something we should remember is this is a turning point as well. Now, remember the shape of a cubic is a mountain and then a valley, but that's for a positive cubic. In this case, we have a negative cubic, and the reason why that is because the x cubed term, all the way here over here on the top right, we found that it has a negative sign out front. So that means we're going to actually have a valley and then a mountain. So imagining how something like that would curve through these points, it's going to look something like this. So we're going to come down, hit that point, and then we have another turning point at 0 and 4. And then we're going to come down and go through that next x-intercept. So that's how you sketch cubic polynomial. We have another question there, and this is in inflection point form. So we can immediately say there's only one turning point, and that's going to be inflection point. So let's write that down. Stationary inflection point at, and the coordinates are h and k, which in this case is -2 and 8. So I'll write that down here. -2 and, well, -2 and -8. So that's our h value and that's our k value. Okay, x-intercept. So we set y equal to 0. When y is equal to 0, we get 0 equal to x plus 2 cubed minus 8. And remember from that table we looked at, this is going to just involve rearranging to solve for x. So we have 8 equals x plus 2 cubed. Take the cube root of both sides. The cube root of 8 is 2. And the cube root of this expression is going to be x plus 2. So that means that x is equal to 0. Okay. Yeah, that looks right. Y-intercept. We set x equal to 0. So we get y is equal to 0 plus 2 cubed minus 8. And that's just going to be 2 cubed minus 8, which is 8 minus 8, which is 0. Again, this is a bit of a redundant information because if we have an x-intercept at x equals 0, then that means that's also going to be our y-intercept. Okay, so let's plot out these 2 points. We have x and y-intercept at the origin there, and then we have our stationary inflection point at -2 and -8, which is going to be down here somewhere. So -2 and -8, and this is going to be 0 and 0. Notice that there's no negative sign in front of our x term here, which means that this is going to be an upright curve. And since we only have one inflection point, one turning point, and that is itself a stationary inflection point, it's going to have this kind of form. Oh, this is a bit hard to draw, but it's going to go through there, it's going to go through the origin there, and then it's just going to keep continuing up to infinity. It's going to look something like that. Alright, so that wraps up our 1-2 revision on linear equations and polynomials. We're going to move into learning about other functions now. Please make sure you're asking questions if you have any questions about what we did there or just any questions about what we've covered so far. Alright, so the first type of function, new function we're going to learn about is the hyperbola. So this has the form y equals a over x minus b plus c. There's going to be a vertical asymptote at x equals b and a horizontal asymptote at y equals c. So here's the graph on the right of y equals 1 over x. Just note that depending on those values of b and c, it's going to kind of shift around, and then a here is going to dilate the graph, so it's going to spread it further away from the y and x axes. Okay, one thing you should know with hyperbola functions is you can use short division to convert it from one form to another. And this makes it a lot easier to work with. So in the previous slide, we looked at this form of a hyperbola, but this is also a hyperbola here. And we can use short division to convert it to this form here on the right, which is a lot similar to what we see in this equation we looked at here. So it's a more digestible form of a hyperbola. So the process for short division, you write out the fraction, in this case x plus 1 over x plus 2. What you then do is you introduce a plus 2 so that you mimic the plus 2 in the denominator. So now we have an x plus 2 term at the top and we have an x plus 2 term at the bottom. You just want to make sure that you subtract the plus 2, so you write minus 2 in the numerator as well, so that the fraction is unchanged overall. What you can then do is split the fraction up into 2 separate fractions, and because you mimicked the plus 2 in the denominator, you can actually reduce this entire fraction down to just a number. So in this case, it's reduces to 1. X plus 2 divided by x plus 2, it all cancels out to 1. And now we have something in the same form as what we looked at in the previous slide. A over x minus b plus c, 1 over negative 1 over x plus 2. Okay, so we'll get a bit of practice with this. I'm going to ignore the first example because it is pretty basic. We'll move straight into the second example here. So 2x minus 3. So we've got 2x minus 3, and we're trying to mimic the plus 1. But notice though that we have a 2 out here at the front. So in fact, what we're trying to mimic is a plus 2, and you'll see why later down the line of working. So we have a plus 2, and then, oh, that's supposed to be a minus. Let me get rid of that. So plus 2, so we added a 2, so we have to subtract a 2. And then we've got the minus 3 at the end there, and then we've got x plus 1. Okay, so we can then split it up. We have 2x plus 2 over x plus 1, and then we have plus, and then we have minus 2 minus 3 over x plus 1. Now notice with this first fraction here, we can rewrite it as 2 and then times x plus 1 over x plus 1. And now you can see there, because I chose to introduce a plus 2 in the numerator earlier on, I've actually ended up with 2 linear factors that I can just cancel out, and that's going to become a 2 in our next line of working. Here on the right, we're going to get minus 5 over x plus 1. So our final answer is going to be minus 5 over x plus 1. So there you go. Again, if you have any questions regarding that, please feel free to ask. We have a truncus now. This is kind of like a hyperbola, except with the hyperbola we had these curves here on opposite sides of the axes. This time they're kind of on the same side of one of the axes. In this case, they're on the same side of the x-axis. So it kind of looks like a volcano. You might be familiar with this from your previous study of 1-2. Same kind of rules, as well as same kind of form for the equation. Just note that you have the x minus b term being squared. As opposed to hyperbola, there's no squared term. Again, vertical asymptote at x equals b, horizontal asymptote at y equals c. Okay, we'll look at some other functions now. First of all, we've got the square root function. So that's the root of x, or x to the half. It's going to have this shape where it starts at the origin. There's nothing on the left side of the x-axis, by the way. It just starts at the origin, then it increases, and then it slowly gets flatter over time, passing through the point 1 and 1. If we have the cube root of x, or x to the third, you're going to have it pass through the origin and kind of have the same shape as a square root graph, except it also has this negative branch down here. So if you imagine what a cubic graph looks like, it's kind of just inverted, and that'll actually tie into what we learn about inverse functions later on. But just note that all the power functions where we have x equals 1 over a, and a is an odd number, in this case it's 3 because we have x to the 1 over 3, it's going to have this general shape. That's the same thing with x to the half actually as well. With this 2 here, if it's any even number, it's going to have this general shape where it's not going to have any negative branch. It's just going to start at the origin and go up and then peter out over time. Now, a general trend as we increase n is that the function is going to, the bigger n is, it's going to rise more drastically from the origin and then peter out over time. So we've got x to the half. You can see that it doesn't rise very drastically, but it still does rise, and then it takes longer to peter out. Whereas x to the 1 over 4, it rises very drastically, and then it slowly, well, it peters out a lot more quickly. Note that all of these graphs will pass through the point 1 and 1. So no matter what n is, whether it's odd or even, as long as it's an integer, it's going to pass through the point 1 and 1, as well as the origin. It's going to pass through the origin. Okay. We're going to move into functions now. So the goal here is to build up our knowledge on function notation. And we're going to start off by first analyzing what a relation is. So this is really basic. It's just a relationship between variables. And we express this through a rule. In this case, we have an example. This is the rule y squared plus x squared equals 1. It's a relation with the variables x and y, and it connects them in some particular way. There's a relationship between them. Now, aside from what we see in the next slide, you don't really have to worry about relations. Just know that from this slide, you want to take away the fact that a relation can take one x value to more than one y value. And again, we'll look in the next slide to figure out more about how that works. A function is a specific type of relation, so it's a subset of relations where only one y value exists per x value. So if you plug in an x value to a function, you're only going to get one y value out. Whereas with a relationship, it can take that x value to more than one y value. It helps to think of it like a machine. So we have a machine here, we put in an input number, and we get one single output. So here's the next slide. So we're looking at relations here. There's 4 different types. You can have many to one, which means that many x values are mapped to a single y value. So for instance, if we look at a y value of 5, so imagine a horizontal line that represents y equals 5. We can have x equals, that could be maybe -2, or we could have x equals 2. So there's 2 x values that map to that one y value. We can have many to many, so many x values map to many y values. In this case, let's pick an x value at this point along the x-axis. This maps to this y value up here as well as this y value down here. And the same thing with y values. If we pick a particular y value, let's say we pick this one up here, it's going to map to this x value as well as this x value. You can have one to many and one to one. The way we can check whether a relationship is a function is, a relation is a function is if we use what's called the vertical line test. If it passes the vertical line test, then it's a function, and if it doesn't pass the test, it's not a function. The way that looks is if we draw out a vertical line at any point along the graph, and it hits the graph more than once, let's say in this case here, then it's not going to be a function, because that means one x value maps to many y values. If we look at this first scenario here though, no matter where we place this horizontal line, it's going to hit only once, so that's a function. Same goes with these other 2 graphs. So that's the way that we tell if a relation is a function. Keep that in mind because there are some questions on the exam that might ask you, how do you test if a relation is a function? And you just mentioned the vertical line test. Okay, the next thing we need to know is the domain and range of a function. So the domain is the number of x values, or the complete set of x values that you can put into the function and get a meaningful result. So it's the input of the function. If we imagine the function as a machine, it's what we put in. The range is the y values that we get out of the function. It's the output of the function. So it's what happens with that particular number when we put it through the function and we get our output. So note that the domain is associated with the x values, whereas the range is associated with the y values that come out. Okay, so moving on to function notation. Again, there's a lot of stuff going on here, so if you have any questions, ask away in the chat. But the first aspect of this notation is this first part here, f. So this is just a name for the function. F is commonly used, it stands for function, but you can also see G and H just because they come next in the alphabet after F. What we're going to see next is the domain. So A represents the domain here. This is going to be the number, the complete set of x values that can be plugged into the function, like we saw in the previous slide here. B is the codomain, but don't worry, this is something that you don't really have to know for methods. Just know that it's called the codomain. Now, f of x followed by a particular rule relating x and y together, that's going to actually be the core of the function itself. It's a rule, it's a machine that turns the inputs, our x values, into our outputs, which are our y values. Okay, so sometimes you might not get this notation. You might just be given the rule. So f of x equals blah, 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 without all this stuff in the front here. In that case, because the domain hasn't been explicitly defined to you, it hasn't been laid out for you, you just assume that it's the maximal domain. So the maximal domain is the complete set of values where if you were to put in a particular number as an input, it would make sense and you could get a valid output. So if we look at a polynomial, let's say x squared, we can put in any real number for x. Any number, whether it's negative 100,000 or 3 or 2.11111, it's going to give us a valid output. It's just going to square that number. So for any polynomial, the maximal domain is the set of real numbers, which we represent by capital R. In some cases, though, especially in some of the functions we've looked at, it doesn't make sense to put in certain values. For instance, 1 over x, the denominator cannot be equal to 0 in a fraction. So if we put x equal to 0, it wouldn't make sense. We wouldn't get a valid output. So the domain of this function is going to be all real values except for 0. Same thing with, well, not the same thing, a little bit different with the square root function. Yeah, whatever's under square root, it can't be less than 0. So that means that the domain of this function is 0 to infinity. We can put any value in for x going from 0 to infinity, just not a negative number. Other functions that have kind of restricted maximal domains is the natural log of x and the tangent of x. You may have had experience with the tangent of x previously, and we're going to look at the natural logarithm of x later in this lecture. We've also got hybrid functions. These are also called piecewise functions, and they're basically set apart from your traditional normal functions by the fact that they have different rules over different x values. So if we're looking at this particular example here, we have this here as being a hybrid function, and the way it looks graphically is this. Other than this distinction where they have different rules over different x values, they're basically the same as normal functions. They'd function as you'd expect. If we wanted to substitute a number into the function, let's say we wanted a substitute in the number 2, we would write f of 2. We'd look at the set of rules here. If x is greater than or equal to 1, in this case 2 is, then we use this rule. So we'd write f of 2 is equal to 2 minus 1 squared minus 1. That's it. There's nothing too complicated about these. Okay, so we're going to do another practice question so we can wrap our head around these hybrid functions a little bit more. The question sets out a hybrid function for us, and we need to find the values of b and c given that f of x is equal to f of negative x. So we know that f of negative x is going to be, let's see, since x is going to be negative, we're going to take this part of the hybrid function here. So we write this out. We're going to put negative x plus 2 squared minus 2. This has to be then equal to the positive part of the function. So this is equal to f of x, negative x plus 2 squared minus 2. But we know f of x is equal to x squared plus bx plus c, because we're taking the positive part, the part that's greater than 0. Then this is going to be equal to negative x plus 2 squared minus 2. Expand out the right side, we're going to get x squared minus 2, oh, not minus 2, sorry. We're going to get minus 4x plus 4 minus 2. And that's going to be x squared minus 4x plus 2. Then we can use that trick we learned earlier, equating coefficients. This implies that b is equal to negative 4 and c is equal to 2. So that's a little bit confusing, I know, so make sure you're asking away questions in the chat, and I'll reply as quickly as I can. Okay, moving on to sum functions. So sum functions are basically just two functions being added together. Now, this might seem like a foreign concept, but in fact, it's something that you've been encountering all along through your study of maths. Something as simple as y equals x plus 1 is a sum function, because we're adding the functions y equals x and y equals 1. If we think graphically about the way this looks as well, just draw out a rudimentary set of axes here. We've got x and y axes. Y equals 1 is going to look like that. So it's just a flat line intersecting at y equals 1. Now y equals x is just going to look like a diagonal line going through the origin. So if we were to add these together, it would look something like that. Right? Because we've got this y equals x, but we're raising all the values up by one value. So it shifts up, and we get something like that. And this aligns with our knowledge of linear functions in general as well, because y equals x plus 1 should have a y-intercept at y equals 1 and an x-intercept at x equals negative 1. So that's sum functions. One thing you should note though is that the domain of a sum function, hx, where hx is equal to fx plus gx, it'll only exist if both f of x is defined and g of x is defined, in which case the domain of h is going to be equal to the overlap between the domain of f and the domain of g, so the intersection between the domain of f and the domain of g. In this case, let's say we have a function f that has this domain along the x-axis, so the x number line, and then we have the domain of g being all of this. So it's just going to be the overlap, which is the domain of h, which is from this point to this point. Okay, so to sketch a sum function, these questions are a little bit tough, and you won't really see them much in the exam. They're usually going to be the really high level differentiator questions, but that's what makes them all the more important to know how to do. So the first step to sketching a sum function is we faintly sketch both functions. We've got a function that we can trial this method with here. We've got x squared plus 1, that's our first part, and then 1 over x plus 2. So x squared minus 1 is going to look a little bit like a parabola, like that. But it is going to look like a parabola. There we go, that's x squared plus 1. We then have 1 over x plus 2. So remembering the formula for a hyperbola, that's going to be just the general case, 1 over x, but we're going to have a vertical asymptote at x equals negative 2. So that's going to be somewhere around here. That's our vertical asymptote. And then we're going to have function looking something like that, and then also something like that. It's a very crude drawing, but imagine this is the hyperbola, that lower left negative branch, as well as this branch up here that peters out over time. Then the second step is to look where one graph is 0, and we keep it, and we look for where they intersect, and we double it. So in fact, with my drawing of the parabola, it's going to go more like that. So the functions intersect right here, so I'm going to double the y value. That means our sum function is going to pass through a point all the way up here. They also intersect right here, so I'm going to double that value. Look for where they intersect. Yeah, double it. Look for when one graph is 0. So the x squared plus 1 graph is 0 at 2 points. So at that point, I'm going to keep it. So I'm going to draw a dot on the other graph right there. And I'm also going to draw a dot there. So all these dots I'm drawing are points that my sum function is going to pass through. Now, I think that's all we can do, to be honest. So, in general, when you're drawing the sum function as well, you just want to keep in mind that it is just the sum of these two different functions. So, in terms of the positive branch here, I'm going to have a line coming down from here, passing through this next dot, and then, let's see, I'm going to have it go under the x-axis a little bit, because you can see the x squared plus 1 graph is going very far down on the on the y-axis, whereas my 1 over x plus 2 graph is very close to the origin. So the x squared plus 1 graph has more influence. So it goes down, and then it's going to come up, and it's going to continue going up along with the parabola. The left branch here is going to look something like, let's see, I think it's just going to be a line going up like this. So you consider the fact that the hyperbola is going down asymptotically, but then eventually the hyperbola flattens out. It gets closer and closer to zero, whereas the parabola skyrockets to infinity. So that's what this represents right here. This is the more complex question, but again, and with these questions as well, you're going to have your CAS there to help you sketch the graph. But it's important to just kind of understand the idea of how two functions sum to make a third. Okay, so we've got a domain question here. We've got two functions. We're finding their maximal domain. So again, remember that the domain of the sum is the overlap of the domain of its constituents. So the domain of f plus g is equal to, that's an equal sign, is equal to the domain of f intersect the domain of g. So that's a rule we looked at earlier. So in this case, it's going to be, what's the domain of f? It's negative infinity and 2, intersect the domain of g, which is, round bracket, negative 2 and infinity. And if we're looking at the overlap for those two, it's going to be negative 2 to 2. And make sure we're using the round bracket and square bracket. So we're looking at the left end of this domain here. In this case, it's round bracket negative 2, and then the right end of this data set here, which is, this domain here, which is 2 followed by a square bracket. So it looks like D is our answer. Okay, there's just a bit of a diagram on how sum functions work. The reason why the domain of the sum function is equal to the overlap between the domains of its constituents is just because we need numbers that can go into both f and g for them to be able to go into h as well. Okay, moving on to composite functions. So I personally hated this topic. It's a very confusing topic, but I'll try my best to simplify it for you guys here. A composite function has one function inside another function. So we can see here h of x is equal to f of g of x. What this means is we put a number into, when we're putting a number into h, what we're actually doing is putting the number into g, so it's being processed by the function g, and then whatever g outputs, that's then going into f. So it looks something like this. We put in a number, it goes into g, gets outputted, then it goes straight into f, and then it gets outputted. And that's the output of the overall function h. Okay, so one thing to note is that numbers coming out of g are going into f. So for h to work, we need to make sure that numbers that are coming out of g are even able to go into f in the first place. Because remember, functions have domains. They have particular x values that they can take in and give a valid output. So what we're essentially looking for is we need to make sure the range of g is a subset, is contained within the domain of f. You can use this little mnemonic, writer, range inner is subset of domain outer. That'll help you remember that rule here. Very important that you know this rule. It always comes up when you're dealing with composite functions. So another thing to note as well is that the domain of the composite function f of g of x is going to be equal to the domain of g of x. And if you spend some time looking at that diagram there, you'll start to realize why. Okay, so the reason why composite functions is such a difficult topic is because often the domain of f is going to be a restriction point that prevents some values coming out of g from going into f. So for f of g of x to be defined, we need the values going out of g to be able to go into f. So what we can do is we can restrict the domain of g so that it's a subset of the domain of f. So that means what's going out of g can go into f. So here's a couple of steps here in terms of how we perform that restriction. And we have a question next where we can apply this to a practice question that you may run, the kind of practice questions you may run into. Just remember these 5 general steps, as well as these statements here. The range of G is a subset of domain of F. This is the subset of sign. Yeah, so those are our 5 steps. We'll apply them to this scenario here. We have a function x squared minus 1. We have a domain which is all real numbers. And then we have g of x, which is root x. So our maximal domain is going to be x is any number 0 or greater. First thing we have to do is show that g of f, this notation means g of f, is not defined, and make a restriction f star so that it is defined. So first we'll tackle this first part of the question. We need to show that g of f is not defined. What we can do is draw out a little table, and it's very crucial that you do this so you don't get muddled up in the different domains and ranges. So looking at f, its domain is all real numbers, so negative infinity to infinity. Its range, if we imagine what a parabola looks like, it looks something like this. So the set of y values that it puts out is going from -1 on the y-axis all the way to positive infinity on the y-axis. So that's its range. Same thing with g. We can only put in positive numbers or 0, so that's its domain. And then its range as well, this is going to output either 0 or a positive number, so that's its range there. For g of f to be defined, we require the range of f to be a subset of the domain of g. So notice that we're using that notation that we talked about in this slide here. Range of g is a subset of domain of f. What we can then say is, but the range of f is negative infinity to infinity, and the domain of g is 0 to infinity. That means that the range of f is not a subset of the domain of g. So it's just the subset sign with a dash through it, similar to the not equal sign. It just means it's not a subset of the domain of g. So you've disproved this statement, and therefore g of f is undefined. I've answered the first part of the question. The second part is make a restriction f star so it's defined. What we then require is, well, we want the range of f star to be a subset of the domain of g. So that means at most, if we're looking at the biggest possible range that f star can have, it would have to be equal to the domain of g. Now the domain of g, as we saw in our table, is 0 to infinity. So we set the range of f star equal to 0 to infinity. Then we draw out the parabola. So we've got the parabola here. We want only the values of x for which, if we put them in, we get values of y that are within this range here that we've set out. That would mean we take values of x either going from 1 to infinity, because anything that we put into the function f star, it'll output a positive value, so it'll be within the range of f that we require, and as such will also be within the domain of G. Or we can take all negative values below -1. You can choose either. And that's the thing about composite function. There's a whole range of different restrictions that you can make to make this function g of x defined. In this case, I just went for the positive branch. So we have the domain of f star equal to 1 and infinity. This is a very complex topic. Feel free to ask questions in the chat about it. But I think even in the chat, it will be quite hard for me to explain. So I'll be honest, it's something that you naturally start to get better at the more practice questions you do. It's about just applying yourself to these questions and getting experience with a broad range of different kinds of composite function questions. So we're done with composite functions now. We can move on to inverse functions. So again, you might be familiar with these from your previous study. Essentially, inverse functions reverse another function. So mathematically, that looks like f inverse of f of x is equal to x. This might look a bit intimidating, but if we think of functions as machines again, let's say that f of x is a doubling function. Whatever we put into the f machine, it's going to double the size of it. So we get these two small cubes, it turns into cubes that are double the size. An inverse function would take these big cubes and turn them back into small cubes. So what's that? It would halve the size of them. So these big cubes are going into the halving function and they turn back into small cubes. Similar thing you can see here. Whatever we put into f, we then get the value f of x as the output of the function f. That output f of x is represented by the big cubes. Then we take that output and we put it back into, or we put it into the inverse function. And that's going to turn it back into what it originally was, which is just x. So you can see this whole expression equals just x. So some key properties, because you find an inverse through swapping the x and y variables, it means that the graphical representation of the inverse function is that it's reflected on the y and x line. Another thing as well is that the domain and range of f of x is going to be swapped when you're looking at the domain and range of the inverse. The domain of the inverse is the range of the original function. Same with the range of the inverse, domain of the original function. Now, in terms of how you find an inverse function, first off, you want to make sure that the function is 1-to-1. So it passes both the horizontal and vertical line tests. But remember, the vertical line test is to test if a relation is a function, and the horizontal line test is to additionally determine if a function is a 1-to-1 function. Then you have to write to invert, swap x and y. Now this counts as working. Vika's very picky about this, so please make sure you write swap x and y in the exam. Then you rewrite the function with x and y swapped, you rearrange to make y the subject, and then you write the rule of the inverse. So let's do it with an example. We have a function 2x cubed plus 1. So to find the inverse, and this is exactly how your working out should look like in the real exam, swap x and y. So we get, oh, actually, before you do any of this, make sure that you mention let y equal h of x. I always forget that step. And a lot of students also forget that step too. Make sure you include that. Let y equals h of x. To find the inverse, swap x and y. And then you write x is equal to 2y 3 plus 1. Then you rearrange for y. That's the next step. So we've got x minus 1. Oh, x minus 1 over 2 is equal to y cubed. You take this cube root of both sides. So we get x minus 1 over 2 cube root of that. And that looks like it. So with isolated y, we can then write, therefore, f inverse of x is equal to, let's see, yeah, is equal to x minus 1 over 2 squared. Notice that it only says find the rule for the inverse function. If it tells you to define the function or define the inverse function H inverse, you also want to find the domain and write it out using function notation. Again, VCAR is very picky about this stuff. Uh, Often what separates the higher achieving students is the fact that they notice that distinction, that it's asked to define the function. In which case you would write something like f inverse going from all real numbers to all real numbers. F inverse of x is equal to the cube root of x minus 1 over 2. Okay, so just a quick note as well, the way I found the domain here, all real numbers, is just by thinking of what the range of the original function h is. So remember, the domain of the inverse function is equal to the range of the original function. In this case, we have a cubic, and the range of cubics is always going to be all real numbers. So that's going to be the domain of R. Again, if you've got any questions about that, ask away in the chat. Okay, so yeah, we can restrict the domain of functions. We've already looked at that though. And then this is just some VCAR examiner notes. You can see here that they explicitly want you to write that you swap x and y to find the inverse. Otherwise, they don't understand how you got from talking about the function itself to suddenly having x and y swapped in your working. You don't need to write make y the subject. You don't need to write y as the inverse of h of x. You can just proceed from this line of working down to this line of working down to this line of working. Just make sure you write for inverse swap y equal to x. Okay. Moving on to transformations. So yeah, we're done with functions, polynomials. This is something a little bit different now, but it's still something that you should be a little bit familiar with, hopefully from your 1-2 study. But if not, we're going to cover it in detail now. Okay, so why are transformations important? The reason transformations are important is because it allows us to manipulate the graph of an equation essentially to our will. We can stretch the graph, we can squeeze the graph, we can move it around on the Cartesian plane. We can do anything we want to the graph. But the reason transformations is important is not only because of that, it's because through our study of transformations, we can understand how those changes are reflected in the actual equation of the graph itself. Are we introducing a minus sign into the graph of the equation? Is that what induces a reflection in the graph of the equation? So throughout this part of the lecture, just keep in mind that the transformation of a graph is very intimately connected with some change in the equation of the graph itself. The first thing we have is dilations, which is where we either stretch or squish a graph, as you can see by that little animation there. Second type of transformation we have is reflections, where we flip it in the x or y axes. In this case, we've got a parabola here, and we're either flipping it in the x-axis, so it turns into a inverted parabola, or we flip it in the y-axis. So in this case, it just looks the same because it's symmetric about the y-axis. And then we have translations, where we move it up or down, left and right, whichever direction. We're not stretching or squeezing or reflecting the graph. All right. In terms of figuring out how each type of transformation is connected to a change in the equation itself, let's first look at dilations. So with a dilation by some factor a, if we're dilating from the y-axis or in the direction of the x-axis, we're going to affect the x values in the original equation. So if you can think about the original equation, you have a particular graph. If we dilate it from the y-axis or in the direction of the x-axis, we're stretching it out, or we're squeezing it horizontally. And because we're moving it in some way horizontally, that means that the x values are going to change, but the y values are going to remain the same. So remember, if we're dilating from the y-axis or in the direction of the x-axis, we affect the x values. Same thing with the y values. If we stretch this way or squeeze this way, we're affecting the y values, but not the x values. Reflections is the same thing, and I'll leave it to you to figure out why. Translation is a little bit different. If we translate by unit C in the positive or negative y direction, or unit C up and down, it means the same thing. We're going to affect the y values, because you can imagine if we have a graph, we move it up or down, the x value is going to stay the same. It's not moving along the x-axis, but it's moving along the y-axis, so the y values get affected. Same thing with the x direction. Okay. So, unless specifically stated, you should always do transformations in this order. Dilations followed by reflections, followed by translations. The reason for this is because if you do a dilation or reflection after a translation, then you change the translation, as well as it can be very confusing to visualize the exact change that occurs if you do a translation first and then dilation or reflection. So always in your working, do it in this order, DRT, Dr. T. There's two methods of actually applying a transformation to an equation. The first method is the coordinate method, and the second is the replacement method. And we're going to first go over the coordinate method, then move into the replacement method. So the coordinate method, this takes a little bit longer, but there's less room for errors. Now, the thing is with the replacement method, it's very quick. It's the way that you should be using it, like at the very end of the year leading up to exams. But when you begin tackling transformation questions, make sure you use the coordinate method, because there's less room for errors and it'll maximize your chances of getting to the right answer at the end. So the first step in the coordinate method is write out an ordered pair. We call this an ordered pair, x and y. This represents the entire set of points on a particular graph. What we then do is we apply our transformations to it. So if we want to dilate by a factor of a from the y-axis, then we're moving all the x values. Remember, this affects the x values if we're dilating from the y-axis. We're moving all the x values by a factor of a, so we write a times x. Same thing with y. If we're dilating from the x-axis by a factor of b, we write b of y. So we're taking this set of points and we're transforming it under those two dilations from the y and x-axis respectively to the point ax and by. Reflecting in the x and y axes, we put a negative sign, and translation up and down or left and right is going to be just adding those quantities c and d by which we're translating. So ultimately we take the point x and y. Under this series of transformations, we get to our transformed graph, which is going to have its entire set of points defined by this these expressions right here within this set of coordinates. So negative ax plus d and negative by plus c. What we then do is we want to come up with some sort of notation for the entire set of points on the transformed graph, just as we have with the original graph. So what we can do is call the entire set of points on the transformed graph x dash and y dash. What this then allows us to do is equate these two expressions. We have negative a times x plus d equal to x dash, because x dash and y dash are equal to this set of coordinates, and same thing with y dash. So we end up with these two expressions. The thing is, with our original equation, which by the way we were given for this particular question, our original equation is expressed in terms of x and y, right? Let's say it's y equals x squared minus 1. We're dealing with x and y, but in this case, the expressions that we have here are in terms of x dash and y dash. So we actually need to rearrange for the x and y hidden away within these expressions. So we can do that. And there we go. We've isolated x and we've isolated y. And we've got some expression in terms of the transformed coordinate. We can then take these expressions for x and y and plug it back to our original function. So if you can imagine y equals fx, we substitute in negative 1 over b times y dash minus c in for y, and f of x becomes f of negative 1 over a times x dash minus d. So these are the 4 general steps that we went over, and this is a bit of an idea of how dilations work. If you want to explore these diagrams a bit more for yourself, you can download the slides and have a look for yourself. Okay, so let's practice using the coordinate method. We've got the steps here on the right, and let's have a look at the function we're dealing with. X squared plus 3x undergoes these 3 transformations. Using the coordinate method, state the transformed function g of x. So first thing we do is we write down our coordinates on our original graph. So we've got x and y. First off, we perform that dilation. So 3 from y-axis and 5 from x-axis. So that means we're dilating from the y-axis by 3, by a factor of 3, so we write 3x. And same with 5 from the x-axis, we write 5y. We then reflect in the y-axis. Remember that affects the x values, so we write negative 3x, 5y. Then we finish off with translation 4 down and 1 right. So we have negative 3x. We're translating 1 unit to the right, so we add 1 to all x values. And then we're translating 4 units down, so we get 5y minus 4. Okay, so what we'll do is we'll write let x. Yeah, so this is the second step in these 4 steps that we have here on the right. We've got let x dash equal negative 3x plus 1 and y dash equal 5y minus 4. We can then rearrange for x and y, not x dash and y dash. So this would be x equals negative x dash minus 1 over 3. So I just rearranged that first expression in my head to isolate x. Here. And then we've got y equals y dash plus 4 over 5. Okay, so now we have our expressions in terms of x and y. We can plug this back into the original equation. So we've got f of x equals x squared plus 3x. This then becomes, let's see, we would get y dash plus 4 over 5 equals negative x dash minus 1 over 3 squared plus 3 negative x dash minus 1 over 3. Okay, let's see. So rearranging this is going to take a lot of time. So I'm just going to skip straight to the answer. But hopefully you guys are pretty good at your algebra. You'll be able to resolve all the square signs there, as well as rearrange accordingly to get y dash on one side. The answer here looks like y prime equals 5 over 9 x minus 1 squared, x dash minus 1 squared, minus 5x dash plus 1. So as your final answer, you would make sure you state the transformed function g. So you write g of x equals 5 over 9 x dash minus 1 squared minus 5 x dash plus 1. Okay, next thing with transformations is you can also do the coordinate method backwards, and that tells you what transformations change one particular function to another function. So we'll do it with an example here. Let's say that we're looking at what transformations take the graph of y equals 1 over 4 x minus 2 squared. Sorry, the other way around. So what transformations take the graph of y equals x squared to y equals 1 over 4 x minus 2 squared? What you do first is you want to try and equate these two functions. And the way you do that is you kind of rearrange it so that it's easier, so that you have the transformed function in the same general form as the original function. So in this case, it looks something like this. You multiply both sides by 4. Now you can see that we've got some expression for y equal to some expression for x squared, which is the same thing we've got here. We've got y equals x squared. Then we can equate the parts. So first of all, we equate y, 4y dash and y. Then second of all, we equate x dash minus 2 and x. So we have these expressions. Then we can rearrange to isolate y dash and x dash, as you can see we've done there. Y dash is y over 4, x dash is x minus 2. But remember that these expressions here for y dash and x dash are actually the expressions for the transformed set of coordinates. So what you can do is straight away deduce what the dilation that's occurred is, or what the transformation that occurred is. So in this case, we've divided every y value on the original graph by 4. So we're dilating by a factor of 1 over 4 from the x-axis. And then in terms of the x coordinates, we're moving every single x value on the original graph 2 units to the right. So that's a translation of 2 units to the right. Now, these are the steps that we just described there. This is the replacement method that we're going to go into. So we've finished covering the coordinate method. Again, remember to always use the coordinate method in your working until you feel very comfortable with it. Then you can start learning using what's called the replacement method. So you can see there's a lot of stuff going on. What we've done is we've taken the expression y equals f of x, and we've introduced all these different variables, and each of these variables does a different thing. It dilates, for instance, a here, it dilates by a factor of a from the x-axis. If a is negative, we're getting a reflection in the x-axis. N here, it dilates by a factor of 1 over n from the y-axis, and when it's negative, it's a reflection in the y-axis, so on and so forth with these other factors b and c. Note here that the order of transformations here is dilations, then reflections, and then translations. So I think it's better we go into an example, and that'll help us better understand what's going on. Okay. So a sequence of transformations map the graph of f to the graph of the function 1 over x. What is this sequence? So in this case, we're going from this graph to this graph here. First of all, what we could do is use the coordinate method. Or what we can do is we can use the replacement method. So first off, we have this 2 in front of the our x here. So going back to here, if we have any number in front of our x, we're dilating by a factor of 1 over that number from the y-axis. So in this case, we're going from 2x down to just x. So that would mean that we're dilating by a factor of 2 from the y-axis. The next thing is we're going from plus 3 to just nothing. So that means that this graph is being translated down 3 units to turn into this graph. So we're translating 3 units down. We've also got another translation going on here, minus 4. And if we go back here, if we have minus b, we're translating b units to the right. So we've got minus 4, we're translating 4 units to the left to get to this graph. There's a lot of double negatives and stuff going on there. And again, that just shows how complicated the replacement method is. So if you don't understand it, uh, it'll be hard for me to explain over the chat box, but just the more questions you do with the coordinate method, the more you'll just become intuitively and familiar with the replacement method as well. And then you can start using it a lot more competently in answering your questions. Okay, so we're all done now with transformations. We're going to move on to logs and exponentials. It's the final part. So exponential functions, they have a very simple form. It's y equals a to the x. A is called the base, and it's any positive number except for 1. If a was 1, then 1 to the x would just be representing a straight line, if you think about it graphically. So there's no kind of exponential growth or decay going on. Now note that since it can be any positive number except 1, it means that a can also be a fraction, e.g. 1/2. So we'll look at what it means for a to be a fraction later on. But for now, just be familiar with the fact it can be any positive number except for 1. Oh, okay. Now in methods, you're going to be introduced to Euler's number. This is pronounced Euler, I know it's weird. And his number is E. Now, this number, it's a transcendental number. So just like pi, it's a number followed by a whole bunch of decimal points. So the way you want to treat this number, first of all, in methods is remember that it represents an actual number. So this number is roughly 2.718. Just remember that it's a number between 2 and 3. That'll get you by. The second thing is because it's an actual number, it's not a variable to be solved for. So just like with pi, which you may have run into when dealing with circular functions, you never actually solve for pi. Pi is a number, it's equal to 3.14. The same thing with Euler's number. Okay, so the one thing that you should know when you're dealing with exponential functions is your index laws. I won't go into these in detail, I'll just assume that you know them, because you should know them from your previous studies. But if not, these are the 6 rules that you'll have to know. Get very familiar with these because you're going to have to be using them a lot in your working out. Keep in mind that some of these rules are derived from other rules already present in the list. So for instance, if we look at rule number 5 here, a to the negative m is 1 over a to the m. This is actually we'll look at number 2. A to the m over a to the n is a to the m minus n. This is a combination of rule number 1 and rule number 5. So a to the m times a to the n is a to the m plus n. If we had a to the negative n here, then that would be 1 over a to the n. So we would get a to the m over a to the n equals a to the m plus minus n, which is just a to the m minus n. I know that doesn't make much sense just saying it out loud, but keep in mind that these rules are very much interconnected, and eventually you'll notice those interconnections for yourself the more you use them. Okay, so in terms of graphing exponential equations, there's a couple of features to the graph. The first thing is that the horizontal asymptote, there's going to be a horizontal asymptote, and it's going to be at y equals 0. You can see that here in the graph of y equals 2 to the x. We also have a y-intercept of 1. No matter what our base is, it's always going to intercept at 1. So remember that. Even if our base is e, or if it's 100,000, going to intercept at 1. Same thing with the domain and range. It's always going to be, the domain is going to be all real numbers. So you can put any number into this function. It's going to give you a valid output. And then the range is going to be 0 to infinity, not inclusive. So you can put in, well, it's going to output any number between 0 and infinity, but it won't output 0 and it won't output infinity. Now, before we move on, just thinking about this asymptote here, why does it exist? And why does the graph approach this asymptote? If we think about it logically, the smaller and smaller number we put into this function y equals 2 to the x, like let's say we put 2 to the negative 100,000. If we do our working out here, um, 2 to the negative 100,000. Using an index law, this is going to be equal to 1 over 2 to the 100,000. We know that this is a huge number, and this is obviously just 1. So 1 divided by a huge number, that's going to give us something very, very close to 0, but not quite 0. It's still going to be a number, just a very, very small number. As we decrease the value of x more and more and more negative, this number is going to get more and more, this power is going to get bigger and bigger, and it's going to get closer and closer to 0. So that's why as we go more and more negative, we're going to approach this value of 0, but we're never going to reach it. So it's an asymptote. Okay. Now, we looked at the basic graph of 2 to the x, or just the basic exponential graph in general. We can now apply transformations to it to have a bit more versatility when it comes to sketching exponential equations. First of all, we can look at reflections. If we reflect in the x-axis, we know that that means going from x comma y to x comma negative y. We're affecting the y values because we're reflecting in the x-axis. So x dash is just x, y dash is now negative y. So again, we have to rearrange for x and y and have an expression in terms of x dash and y dash. So we have x is equal to x dash, y is equal to negative y dash. Substitute those into the original equation. In this case, our original equation is y is equal to e to the x. So we're going to end up with y dash is equal to negative e to the x. So that's that blue graph there. That's what y equals e to the negative x looks like. Same thing with reflecting in the y-axis. We get y equals e to the negative x. Now I just want to explore this scenario a little bit more. So we're reflecting in the y-axis. We get y equals e to the negative x. Let's apply a couple of index laws to it. So we have a to the m times n is equal to a to the m to the n. So taking our expression y equals e to the negative x, we can separate it into it equaling e to the negative 1 to the x. Then we can apply the second index law here to change e to the negative 1 to 1 over e. So actually what this green graph is, while it is still the graph of e to the negative x, it's actually the graph of 1 over e to the x. So whenever you see a fraction as the base in an exponential equation, you want to think of index laws. And in terms of thinking about it graphically, you want to think of it being reflected in the y-axis. Now, obviously, you can have a whole range of transformations. Here I've sketched out y equals negative 3e to the 2x plus 1. But in general, the thing you want to make sure that you know when sketching the graph is, first of all, you know the x and y intercepts. You find those just by setting x and y equal to 0, or y and x equal to 0, respectively. And then the horizontal asymptote, you can ascertain pretty easily because if there's any translation up or down, that's the only kind of transformation that's going to affect the horizontal asymptote. And that's going to be very clearly visible out the side of the equation. So you can see here it's plus 1. So the horizontal asymptote is y equals 1. Okay, so, oh, there we go. When it comes to solving exponential equations, there's a couple tricks that you can use. The first thing you can do is make each side the same base. So you can combine everything into one base on each side and then equate the powers. So that is, if a to the x is equal to a to the y, it follows that x is equal to y. That's a trick that you can use. Another trick you can use is you can recognize that the equation is in a quadratic form and then apply your knowledge of quadratics to solve it. So for instance, if we have this equation here equal to 0, we can let a equal to 2x, or 2 to the x, and then notice that if we substitute in a here, we're actually going to get a squared plus 3a plus 6. That's just a quadratic, we can solve that. Then we can substitute 2 to the x back in for a. That's one thing you can do. And the last thing that you pretty much will always be doing is make sure you use your index laws. Whenever you're dealing with exponentials, always use your index laws. Uh, of course, all of these tricks don't really make sense without putting it into some sort of context. So we're going to do a practice question here, so that we can try out some of those tricks. We have 2 to the 3x minus 3 is equal to 8 to the 2 minus x. So what we can do is use that very first trick we saw in the previous slide. 8 is equal to 2 to the 3. So this expression on the left is equal to 2 to the 3 to the 2 minus x. Applying an index law, we can write that 2 is equal to 3 times 2 minus x. So that's the law where a to the m to the n is equal to a to the m times n. We can expand out that little 3 there, so we get 2 is equal to, that's 6 minus 3x. And all of this is equal to 2 to the 3x minus 3. What this then implies, because these exponential equations have the same base, is that their powers are equal. So 3 to the x minus 3 is equal to 6 minus 3x. Then we can just solve for x. So in this case, I'll add 3x to both sides, we get 6x, and then I'll add 3 to both sides, so we get 9. X is equal to 3 over 2. And of course, you can substitute x back into the original equation to make sure that everything adds up. Okay, and we'll get some practice with sketching as well. So we have y is equal to 1 over 4 to the x minus 2. So remember, whenever we have a fraction, we want to think index laws. We can rewrite this as y to the 4 to the negative x minus 2. Okay, so you can think about transformations, and that'll allow you to solve it immediately. Or you can find the x and y intercepts by hand, which is what I'm going to do. And I suggest you do it for the exam as well. So we set x-intercept when y is equal to 0. 0 is equal to 4 to the negative x minus 2. That means 2 is equal to 4 to the negative x. Again, we have to use that little trick. 2 squared to the negative x. That's 2 to the negative 2x. So that implies that 1, so we've got a power of 1 here, is equal to negative 2 to the x, or negative 2x. So x is negative 1 over 2. So x-intercept, y-intercept, we set x equal to 0. This is pretty basic. Y is equal to 4 to the negative 0 minus 2. 4 to the negative 0 is just 4 to the 0, and anything to the 0 is 1. So we have 1 minus 2, which is negative 1. So we'll plot these points out. The other thing we want to consider is the horizontal asymptote, which in this case we have a translation of 2 units down, so it's going to be y equals negative 2. So we'll draw out our asymptote crudely there. There you go, y equals negative 2. We know that the graph passes first of all through y equals negative 1, which is about there. That's going to be 0, negative 1, as well as x equals negative half. So that's negative half and 0. Notice that I've used an arrow there to point to, oh, there's a glitch that's just happened. I've used an arrow to point to the dot so that my coordinates don't get in the way of the graph that I'm about to sketch. You can do that in the exam. The examiners are fine with that. Okay, so the last thing I want to consider is just the general shape of the graph. Again, I know that the graph is having a fraction to a power, so it's going to be that general shape of the exponential graph, but just reflected in the y-axis. So it's going to look something like this. It's going to head through that point, and then approach our asymptote without ever touching it. Make sure in your exam, whenever sketching exponential equations, that your graph never touches the asymptote. Otherwise, it's no longer an asymptote. We have another graph there. but if you can sketch this one, you'll be able to sketch that one, so we'll move on. So exponential functions, they have a whole range of applications, and often in an exam, you're going to have a question using exponential functions as part of some kind of application question. So either you can have bacteria numbers, you can model that using exponential growth, because one bacteria multiplies into two bacteria will multiply into four to 8, 16. So that's the powers of 2. That's exponential growth. The temperature of a cooling cake, or just a cooling object in general, that's going to follow exponential decay. In general, you're going to have it take this form here, y equals y naught times b to the kt. But you need to check the question. Often in the question, there might be an extra variable that you have to introduce there aside from b, k, and y naught. As well as in some questions, they'll just give you the form of the equation and then give you some information about the scenario and then ask you to find the rule describing that particular scenario. We'll do a practice question to think about it. There's some extra info there. I'm just going to move past it. So here's the question. A temperature of a room was 10 degrees before Peter put the heater on. After 2 minutes, the room was 10 root 2 degrees. An equation that models the temperature t minutes after turning on the heater is T equals T naught times 2 to the kt. What are the values of T naught and K? Okay, so first of all, we know that when T equals 0, so when Peter turns the heater on, T, the temperature, is 10 degrees. So that means, substituting our values into the equation, T equals T naught times 2 to the kt, we have 10 equal to T naught times 2 to the k times 0. This then becomes T naught times 2 to the 0, which is 1, so it's just T naught. So we get that T naught is equal to 10. We've answered the first part of the question. What are the values of T naught? The second thing is we need to find K, and that's where we use the second piece of info. So when T equals 2, so after 2 minutes, the room temperature is 10 root 2. So T equals 10 root 2. Again, we substitute that in, substituting also our value for T naught. So 10 root 2 is equal to 10 times 2 to the k2. So that's equal to 10 times 2 to the 2k. We divide both sides by 10. So we get root 2 is equal to 2 to the 2k. Now root 2 is just 2 to the half. And we get 2 to the 2k. So now we can equate the powers because the bases are the same. We get half is equal to 2k. So k is equal to a quarter. So divide both sides by 2. Okay. We now have logarithms. This is the final stretch. We're almost there. They're defined as the inverse of exponential functions. So, like I mentioned earlier in the lecture, the inverse, the logarithm, it's very helpful to understand it as the inverse of an exponential function because oftentimes you're going to be using this identity here. So a to the x is equal to b. We're familiar with that. That's exponential function. What that equivalently means is that the logarithm of a of b, I never know how to say this, but don't worry, you won't be tested on that, is equal to x. So recall that an inverse function essentially undoes a given function. You can see here that we're taking an x value to a b value in the case of an exponential function. So we're taking this x value, we're putting it to the power of something, and that gives us a b value. That's our output, that's our range. What a inverse function would then do, and that's what the log function does, is it'll take this b value as an input, and it'll spit back the original x value. So it undoes the function that the exponential function does to the x. So now a is known as the base, just as a is the base in the exponential function here. A is also the base in the logarithm. Logarithms with base e are known as the natural log, and they can be written either as logarithm with a small e and then x, or they can be written as ln of x. You can use either notation in the exam. Vika's fine with either. I personally used ln um, because it's just less letters to write, so it'll save time. And I would really encourage that you get into the habit of working with the natural log as opposed to logs in other bases such as log 2. And the reason for that, it goes into calculus and integration and differentiation. Uh, so you'll learn that later in the year. But just get into the habit of working with it now because it'll be helpful at that period of time later on. Okay, so these are our list of log laws. A lot of these are derived from the index laws, but it's good to know them just as a standalone set of laws. The ones I want you to focus on are these two right here, which are basically properties of the inverse function. So you can see here the log of a to the x just gives back x. And a to the log of x is x. That's just properties of the inverse function. I also want you to focus on this here. The log with any base of b is going to be the log of any other base of b over the log of that same base of a. And if we focus on those last two rules I just talked about, the first one you can see here that we just talked about. Equivalently, you can say, or you can express any logarithm with a base a of b. You can express it as the natural log of b over the natural log of a. This is a very useful trick. And that's the second thing with well, it's kind of the same thing with the second rule here, relating it to the natural log. You can have the natural log of e to the x be equal to the, well, e to the natural log of x, and that's all just equal to x. So two very useful tricks that you're going to be using a lot. In terms of sketching, because it's an inverse function, it's just the exponential function reflected in the line y equals x. Remember, the exponential function looked a bit like, let me draw it out, like that. So if you can imagine the line y equals x, we're just reflecting every single point along that line. So instead of a horizontal asymptote at x equals 0, we now have a vertical asymptote at x equals 0. X-intercept of 1 and a domain of 0 to infinity, range of r. Remember, that's just because of it's an inverse function of the exponential function. We're just swapping the domain and range of the exponential function. Again, it's good to think about why the asymptote exists. First of all, we can explain it because it's the inverse function of the exponential function. So if the exponential function has an asymptote, then the log function also should have an asymptote. Another way we can explain it is just by thinking about what happens when we take smaller and smaller numbers, well, the logarithm of smaller and smaller numbers. So let's say, actually, let's not use ln. Let's say log 2 of 0.0001, something very close to 0. What this equivalently means by definition of the log function is if this is equal to some number x, we're doing 2 to the x is equal to 0.00001. And the only way we can have 2 to the x be a very small number is if this x itself is a very, very low number, very far into the negatives. So imagine we had 2 to the negative 100. This would be equal to 1 over 2 to the 100. And again, 1 divided by a very big number, that's going to be equal to a very small number. So that's why the asymptote exists. Moving on, we can sketch some graphs for logarithms just to get an idea of how they work. In this case, I'm just going to show you the power of transformations here. Instead of looking for the x and y intercepts and everything, we can notice here the only transformation being applied is that it's being translated 3 units to the right. So our vertical asymptote will not be x equals 0, it'll be x equal 3. And notice here that we have an x-intercept of 1 for the general graph. And if we're translating 3 units to the right, that means that x-intercept is going to go to 4. So we're going to have this be 4. And that's really all the information we need to provide. Uh, I'll leave that one for now because we are running low on time. When it comes to solving logarithm equations, these are the tricks that I found myself using the most. The logarithm of one number, if it's equal to the logarithm of another variable, then you can equate those variables. Uh, that the property of inverse functions that we looked at earlier, e to the ln of x is equal to the ln of e to the x equals x. That's very important. Using the definition of the natural log, so y equals natural log of x, that implies that e to the y is equal to x. And then we've got this last one here, which is just, it's called the change of base rule. It allows you to change the base from a to, in this case, the natural log, which is e. Okay, now note that when you're solving exponential equations, it's very often going to involve using logs. And when you're solving the log equations, you're going to also be using exponents, and so index rules. As a rule of thumb, when you're solving exponential equations, usually you're going to have to take the natural log of both sides, and then you're going to start having to apply log laws in addition with your index laws, or you're going to incite the log at the very end of your working. For instance, if you end up with your last line of working being e to the x equals 4, then by definition of log, you would state that x is equal to the natural log of 4. When you're solving log equations, in terms of getting involved with exponents, you usually will incite the exponential at the very end of your working. So for instance, if you have the natural log of x is equal to 4 and we're solving for x, then your last line of working would be saying that x is equal to e to the 4. And you're going to do all of this in conjunction with using your log laws, obviously, because it's a log equation. I have a last practice question here. I'm just going to speed through it. Feel free to be asking questions in the meantime. So we have this expression here. This is just practice using your log laws, basically. So this is going to be equal to, we're going to have log 2. When you have two logs being subtracted by one another, it means that you can introduce a division sign between them. So 6 minus x over 4 minus x is equal to 2. And 2 we can also express as log 2 of 4, because remember what the statement means is that 2 to the 2, and that's where we're getting that 2 from, is equal to 4. So we can write that, and because we have the same base logarithm, we can equate whatever's inside the bracket, whatever the input of the logarithm is. 6 minus x equals to 4 minus x equals 4. Then it's just simple algebra. So we have 6 minus x is equal to 4 times 4 minus x, which is 16 minus 4x. I'm going to move the 4x to the other side. We get 3x on that side. And then I'm going to subtract 6 from both sides. So we get 10. X is equal to 10 over 3. All right. Yes, this is a VCAR question. It's worth 2 marks. So it's important to know all those little log laws. So the last little exercise. This kind of question you most likely won't get on the exam. In fact, I think I took it from a textbook, but it's very good practice to just use your little those little log tricks that we explored earlier. So we have log base r of p equals q and log base q of r equals p. We have to show that log base q of p equals pq. So we start off by stating what pq means using our given knowledge here. We know that this is going to be equal to log base q of r, because p is equal to log base q of r, times log base r of p, because q is equal to log base r of p. What we can then do is use another formula that we explored earlier. So we get natural log of r over the natural log of q times the natural log of p over the natural log of r. And so you can see how this trick is very useful. because it essentially takes the question from involving a whole bunch of different bases and different variables to all being united by the fact that they share the same base. In this case, the base of the natural logarithm, which is e. You can notice here we've got natural log of r expressed in the numerator and denominator. So we can remove those. We can write ln p over ln q. And then again, we can use that trick that we just used before to rewrite this as log base q, because we have a q here, of p. And that is the answer that we're looking for, as required. Okay, so we're all done now. We've got through all the content, so good on you all for sticking around for so long. I'm just going to go into a bit of bonus content here. We've gone through all the content, the study design, I mean. So if you want to click off now, you can. Thank you so much for coming. But if you want to stick around for just a little bit of this bonus content, this will help you just know how to lay out your working as well as use your bound reference and everything. I'm going to go into that. So when it comes to laying out your working, there's many different ways to go about it, but often students are kind of under the impression that there's only one correct way to go about it, and they want someone to kind of guide them with the way they should lay out their working. So that's what I'm going to do here. I'm just going to show you the way that I laid out my working while I was studying methods, and I mean the way that worked for the examiners. So first thing is, you shouldn't be afraid to use actual English words to signpost your working out. So I went through my bound reference and saw some annotated solutions that I wrote all the way back in 2022. Some common phrases I would use was things like by observation. Oh, whoops. So by observation, and then I make an observation. A of x strictly increases, A increases. The graphs are now symmetric about the line y equals x plus 1. Some shorter phrases I commonly use was we require that, x is given by y, or as required, as you just saw us use in this previous question. So here I just took an annotated solution straight out of my bound reference and put it into the PowerPoint. This was my exact working for one of the questions, and you can see there's more actual words than working out. Now the thing is, while you don't require words to get full marks on the exam, it's really good because it helps the examiner figure out what's going on with your working. It signposts your working out, as well as it encourages you to be neat with your working. Section it off into different sections, where in each section you're achieving a particular task that eventually gets you closer to answering the overall question. And obviously encouraging neat working, well, having neat working is very good when it comes to the exam because you only have a limited space to be writing your answers. And so you want to make sure that you're organizing your working to fit in that space. The next thing is you should be comfortable with mathematical notation used to signpost working and or otherwise just compact your working down. One that I used a lot was therefore. There's not really any general like rules on how you should use this. You can just use it as much as you want. For instance, every single line of working, you can basically just put therefore before it and it'll still be mathematically correct. The second thing is you can use this right arrow, which means implies that. And I would use this when I was invoking a theorem. For instance, in this example here, I'm invoking the null factor theorem or some kind of mathematical fact, such as an index law, or when you're just making any other logical conclusion. So over time, you'll learn what comes under the scope of those logical conclusions. It's not just limited to theorems or mathematical facts. You can also use the double-ended arrow, which means if and only if. And I would principally use this to just skip a whole bunch of intermediate algebra steps, which I was aware that like it wouldn't be worth any marks. For instance, if you look at this example here, we've got 1 over 1 minus p minus 1 is greater than 0. I could write out all my steps rearranging for p, or I could just use the if and only if sign and straight away state that 0 is smaller than p is smaller than 1. So it helps save a lot of time. Often in the exam, uh, the examiners are just looking for you to make certain statements along the way in your working, and you won't actually get any points for knowing how to, like add 3 to both sides in a line of working out. Um, and the last thing is just knowing that this means is an element of. So you might see this sign whenever you're talking about the domain of a function or something. It might say x is an element of all real numbers. Just be familiar with that. And the last thing is to underline important conclusions throughout your working and box your final answer. In your final answer, make sure you include units, and sometimes the final answer you need to write it in a full sentence so as to answer the question appropriately. In this question, it's asking about the total distance. So you can see here, I figure out what x is, and I find that x is equal to 80. So that's some important info. So I'm going to underline it. The total distance is given by 2 times x, which is, in this case, 160. So I found that 160 is the total distance. In hindsight, I probably should have underlined this. But in my final answer, I need to write it in a full sentence with units to address what the question is asking. What is the total distance? So I'll write that the total distance is 160 kilometers and box that answer so that the examiner can find it quickly. There's the advice just to send you away with. Make sure you keep all this in mind whenever you sit down to study methods and the way you approach studying methods. And then just some bound reference tips. You got to make sure that your pages are permanently bound. You shouldn't have perforated pages, nothing sticking out. In general, if you're careful with the way you make your bound reference, naturally you're not going to have any pages sticking out or perforated pages or just in general bound reference that's not presented neatly. Here's a couple tips for what you can put in your bound reference. In general, I would just use the last two. This was it. I wouldn't use any color or anything. I would just include any tricky questions that I couldn't answer when I sat down to answer them. And then what I would do is I would go into my bound reference, I would copy that question, and then I'll also copy the answer into my bound reference. You can glue your past papers and SACs into your bound reference too. Common mistakes and shortcuts, calculator shortcuts, these are also important. Make sure that you're annotating your solutions along the way with any common mistakes that you're making and any shortcuts, calculator shortcuts that might be applicable to solving that particular question. But again, this is just a guideline. For instance, I only use these last 2 points. You might only use the first two. So just mix and match, find something you're comfortable with. All right, so yeah, that brings us to the end. This is what we covered today, and I'll give you guys a last opportunity to ask a few questions. I'll be there for a few more minutes to answer them in the chat. But if not, hope you guys enjoyed the lecture, you learned something from it. I'll be away teaching on TuteSmart, so make sure you check out TuteSmart and atarnotes.com for all the resources that we offer. Yeah, that's it. Thank you so much for coming. Have a good one, guys.